Hello, it's Stephen Eshiba, and I'm here to help you out with the in-class activities on the Delocalization and Chemical Structure CGI. So the first part one here is to calculate properties of ethene, ethyne, nitrogen dioxide, and so on. So I'm just going to take us straight to Spartan. Now, a number of these you'll be able to just pick up out of Cactus. So, for example, ethene. It knows about that, and so you'll be able to carry out the usual calculations at the semi-empirical level. And let's see if I can show you one more here. If I use Cactus to pick up NO2, then there we go. There's NO2. Cactus does know it. I just wanted to show you that the calculations on NO2, well, we'll do it at the semi-empirical level, but don't forget that since NO2 has an unpaired electron, you would specify that right there. So now I've already calculated NO2, so I'm going to just show you my results and just show you a few other things that you can do. Well, for one thing, bond distances you can get with this little question mark here. So if I want to know the bond distance between that oxygen and that nitrogen, I look down here and it looks like it's 1.18, and you can do that with any pair, 1.18 angstroms. If you want to look at the bond angles, we go up to here, and there you have to pick up, you have to click on 3 atoms. And so now it's told us that the angle is 137.66. And there's another thing that you can display, which we can go ahead and do on this one, is to look at the charges, the partial charges. So for that we go to Properties, and I'm just going to move the box to the side because when I click on single atoms, this will change. So for example, when I click on this oxygen and I'm at this Properties window, it says that the oxygen has a minus 0.4 charge, and if you'll recall, you probably predicted a minus 0.5 charge when you did this prediction, and so there's the charge on the other oxygen and on the nitrogen. Okay, and let's see. Well, and once you've actually done the calculations on these, you can go to this ladder of orbital energies, and we can start looking at the molecular orbitals, for which I generally like to put it on mesh. And once again, we'll just look at the A column here, not the B column. And don't forget that once you clicked over here, you can just use your up and down arrows to go to different ones. So what we're looking for in this now is our orbitals that have pi symmetry, and I'll just kind of show you what that looks like. These look like they have sigma symmetry in the sense of that between that nitrogen and that oxygen, there's approximately symmetry about that internuclear axis. So we don't want that one. We're looking for things that look like pi's. And if you look at it end on end like this, then it'll be pretty obvious here. There we go. There is a pi symmetry molecular orbital. Looks like a bonding one, and it's got this energy right here, minus 18 electron volts. There's another sigma or sigma star. Oh, there's another pi, and it's interesting. We'll go up one more to the next pi, and there's the third pi orbital. So you notice what happens is that this pi orbital has, if you look at it at this angle, it's got 2 nodes in it, and this one only has 1 node in it, and this one doesn't have any nodes in it. I'm not counting the node that separates the blue from the red in the first place. So that's kind of what you'll be doing for a lot of the molecules and atoms.